Hello, everybody, and welcome back. Today we'll be talking about discontinuities and what that entails. So, why exactly are discontinuities important for calculus? Discontinuities are what forces us to use the topic of limits. When a function is not defined at a certain value, we can kind of estimate or kind of find the value as to what y value this function is approaching at a certain x value. So let's go in and talk about the subtopics or the sub-discontinuities that we have. So let's start off by listing them out. We have removable, and we have non-removable. So these are the two major types of discontinuities that we will be presented with in any situation. Okay, so an example of a removable discontinuity would be a hole. And why do we call this a removable discontinuity? Why not just a discontinuity? A removable discontinuity entails that this function can be quote unquote patched with another point placed in. So that hole can just be taken care of by placing another point at that value to fill up that gap. So let's take an example. Let's use the same example that we used in the last video where we have y equals 3, but let's change it up y equals x, and let's change it up. What I meant by that was x cannot equal 3. So now let's quickly draw out y equals x. This is the y equals x graph. Let's define our 3 right here, our x equals 3, and we know that there is a discontinuity there because of the notation where we have right here, we have x cannot equal 3. So I'm going to quickly erase that portion here and draw a circle. So we have a hole there. Now that would be an example of a removable discontinuity. Now, when we are trying to figure out what y is at x equals 3, that's not exactly possible because when you plug that into the equation, we should have no value there, so therefore it does not exist. Now let's go in and talk about the removable discontinuities that might be present, the non-removable ones. Number one, you might have quote-unquote jump. So this isn't a formal definition of what this discontinuity is. There exactly isn't a name for it. So I like to call it a jump discontinuity. When you are trying to formally describe it in terms of calculus terms and you're trying to answer a question as to why a certain graph is not has a discontinuity, you wouldn't use the term jump, nor would you use the term hole, or any of the other formal things such as oscillation that I'll be talking about and asymptotes. You would have to describe it using calculus terms, which I'll be getting into in the next couple of videos after talking about what limits are, their notations, how to solve limits, and so on and so forth. So that would be further down the line where you might be asked to say why it is discontinuous or prove its continuity. And then next you would have asymptotes. And lastly, you have oscillations. Okay, now let's talk about these different types of non-removable discontinuities. Just quickly draw out a sketch of a graph of some sort here, and we won't even give it a function value or define it by saying y is equal to, and this will be a piecewise function just to show you exactly what each of these might be. So you might have a function that goes like this, and you have the point defined here, but once you are at this point, there is no value, and might be going down. So this is where you might have a jump, like you can see right here, and the graph is moving from one value to another without being continuous. So this would be a quote-unquote jump discontinuity. Once again, please do not say this in your explanation, in your formal explanation. If you're given that question about why a certain function is not continuous, we will be getting into that later. Now let's talk about what an asymptote might entail. So this might be, maybe you're dealing with a tangent graph in which the line goes underneath, so I might have to shift my x-axis here really quickly. I'll shift this to the middle. And you might have your tangent graph like this. Note this isn't exactly a tan equation. And you have an asymptote, and you have another line, and so on and so forth. So this asymptote that you're presented with here is your discontinuity. Okay, and let's talk about what an oscillation might look like. So an oscillation might look something like this, where you have a graph, sorry about that, that's perfectly normal. It might be going normally, and at a certain x value, it might look like it's at two different points because of its oscillation. So it might look something like this really quickly, and then it continues on and on. So in this case, where you have that oscillation present, it is a discontinuity because it looks like it is in two places at the same time, which is not possible. So for that reason, it's discontinuous. Plugging it into the equation would also yield you with a value that does not actually exist. So that is discontinuities in a nutshell. I'll see you guys in the next video.